Hi, Nick McQuaid here for iste782 Visual Analytics with the textbook R for Data Science, Part 1, Chapter 3, the dplyr library. And we're going to skip Chapter 2 of the textbook because it's very basic, but it is worth reviewing a few of those basics. So the first one I want to make sure you know is the seek function makes a sequence. So this is going to result in x being a vector of 1 through 6. And there are a number of things that we can do to investigate x. We can find out the type of x. We'll get the result of integer here because x is a vector of integers. The length of x is 6 because there are 6 integers in x. The attributes are null because x is a very simple object. It doesn't have any attributes. This is really useful for more complicated objects. And structure of x is just going to give us a very compact representation of the structure of x. And it'll be obvious that it's a vector of the sequence 1 through 6. The C function means to combine or concatenate into a vector. And so this vector y is the same thing now as x. This gives us the same result as saying seek 1 through 6. And if we test for equality, the test will return 6 copies of the word true. 1 because 1 is equal to 1, 1 because 2 is equal to 2, and so on through the list. So typing this expression into R will give us the word true repeated 6 times. We can force y to be integers, even if they're not, by adding an L after the numeral. And if we do that, they're still going to be equal. And nesting doesn't alter a vector. So if we do this in this sort of nested-looking flat fashion, the vector is still flat, and x is still going to be equal to y. We can save the result of this expression in a new variable called z. Z is now a vector of the word true repeated 6 times. It's a logical vector. If we ask the type of z, it'll return logical. If we ask is numeric, it will say no, false. It's not numeric, but true can be coerced to 1, false to 0. So if we say as numeric z, we'll get a vector of all 1s. But still, if we ask the type of z, we'll get the type of is logical. And we could, though, say, we could save this as z, say z gets as numeric z, and then if we did type of, we would get int. Another thing we can do is add a couple of vectors together. If we do that, so x and y are 1, 2, 3, 4, 5, 6. So if we do that, we get a new vector that's 2, 4, 6, 8, 10, 12. The first 3 locations in z, which are going to be 2, 4, and 6. This is also the first 3 locations in z, also 2, 4, and 6. All the locations in z that are greater than 7, this is going to be 8, 10, and 12. And so that's so much for the basics. Let's go on to dplyr. So this chapter covers 6 functions. So there's the function filter, which picks rows by value. Arrange, rearranges rows. Select, picks columns by name. Mutate, creates new columns. Summarize, collapses rows. Group by changes the scope of the preceding 5. So for example, we can particularly use this with summarize. I'll show you a couple of examples of that. So I'd like to show you just a few examples of each of these. There's a section on each one of them, and I'm just going to go over a few of the examples in each one. And you have to load tidyverse, and then you're also going to need to load NYC Flights 13, which is a data set. It's a data set of all the flights, all the commercial flights from the 3 New York City airports, New York City area airports, Newark, LaGuardia, and JFK in the year 2013. And we're going to just use that a lot. So the first of the 6 functions is filter. So here's an example. This is the same example on each row here. The first time through, we're going to just display it. The second time through, we're going to assign it to a variable. The third time through, we're going to both display it, which the parentheses cause us to do, and assign to a variable. Okay, and what we're going to do is filter the flights. So the flights table is in the New York City Flights 13 data set. This is a list of about 336,000 flights from originating from New York City in the year 2013. And we're going to get all the ones that originated on January 1st from the airport LaGuardia. And then we can save that filter result in a variable, or we can save it to a variable and display it. And we can use Boolean operations. So we have the AND operation. So we can say month equals 1 and not day is not equal to 1, or month equals 1 and day equals 1. Month equals 1 or day equals 1. And this is exclusive or month equals 1 or day equals 1, but not both. In this case is not both. We can implement De Morgan's laws, which are always painful to recite. Let me see if I can do it. Let's see, the negation of the conjunction means the disjunction of the negations. The negation of the disjunction means the conjunction of the negations. Ugh. So if you've taken any probability or set theory, discrete mathematics, etc., you will be familiar with Morgan's laws, and you need to use them, but that doesn't make them any less painful to recite. Okay, so there are some exercises for filter, and I've just included some of the solutions here. Arrival delay greater than 120 minutes. Destination is either of the two airports in Houston, Texas. Carrier is one of these three. So there's a separate table within NYC Flights 13 called Airlines that lists all the two-letter abbreviations for the carriers. There are about a dozen carriers or so. Then there are months. So this is going to return all the flights that happened in July, August, and September. All the flights that had a departure delay of 0 and an arrival delay greater than 120. So that's a little scary. They were running on fumes there. Delay greater than 60 and departure delay minus arrival delay greater than 30. That means they made up a lot of time in the air. Departure time equals 2400, so that's midnight, and departure time equals 6 a.m. So that's all the flights between midnight and 6 a.m. Flights between month 7 and month 9, that's going to give us the exact same result as this one, month 7, 8, and 9. And is NA depth time is going to give us all the flights that were not canceled. So if depth time is NA, that typically means the flight was canceled. The second of the 6 functions is arrange. So the arrange function sorts by named columns, with each named column breaking any ties in preceding columns. So we can arrange the flights table by year first, then by month, then by day. So that's the typical time order that we would expect them to be sorted in. Descending sorts in reverse order, so we can sort in reverse arrival delay. So this will give us the largest arrival delays first. Some arrange exercises. This second line is the first exercise. I just did this to verify that that this worked. So is in a depth time simply sorts by whether or not depth time. It sorts in the depth by depth time or by whether the depth time is NA. And so sorting by descending is NA depth time gives the canceled flights first. Descending departure delay, ascending departure delay, This is speed in miles per hour, so this is distance in miles over time in minutes times 60. Descending distance and ascending distance. The third of the 6 functions is select. This picks columns by name, just like select in SQL. And it picks here the year, month, and day, so it just selects those 3 columns. This selects all the columns between year and day. Minus selects all the columns except year through day. So notice that the order of the columns matters here. Here's a helper function, so there are about 6 or so helper functions. Starts with dep, gives us the name starts with this string. So this is just a string that the name starts with, and it's by default it's case insensitive. You can actually make it case sensitive. I think on the next slide I show how you can make it case sensitive. Oh, maybe not. I'll show you at some point here. Let's see. Yeah, there it is. Okay, a couple slides later, I'll show you. So it ends with time, contains these are just strings. Here's a regular expression, matches this regular expression. We haven't talked about regular expressions yet. This is a regular expression. The dot stands for any character. The parentheses cause a group. \1 is a back reference to a group. And because backslash is a special character, you have to prepend it with another backslash. So what this means is a pair of repeated characters. So for example, it would pick up this pair of repeated characters, or this pair of repeated characters, and so on. Okay, so, oops. Let's see, select kills all unnamed columns. Oh, okay, so this is just selecting, using select to rename. So you can use select to rename, but you're only going to get as a result the renamed columns. The other columns aren't going to be returned in the result. So if you want all the columns, if you don't want all the columns, this is fine. Maybe it's a stretch to say it kills them because your data set is still there. It's just the output of the data set is just going to be tail num in this case. So a better way to do it for most purposes is going to be to use the rename function. If you use the rename function, you'll get all of the original columns plus tail num as a new data frame. Rearrange columns. So this gives us airtime followed by everything. So everything is, you might think would include airtime, but select will only take a column one time. And we'll see that, I think, on the next slide here. So we can give carrier 3 times. It's only going to return 1 carrier column. Another helper function. So these other helper functions are one of and contains, and you can get help on them. You can get documentation by getting help select helpers. One of just returns these columns. So this is the same thing as what we did at first, saying select year, month, day. This selects something that contains the string time, case insensitive, but we can make it case sensitive. So Jeffrey Arnold, who's written a lot of interesting R code, also has an online solutions website for this book in which he points out that you can use ignore case here. Mutate, the fourth of 6 functions. So this adds new columns that are functions of existing columns. So first we're going to create a small data set that's got fewer columns than flights. It's just got the year, month, day, departure delay and arrival delay, distance and airtime. And then we're going to mutate that by adding these 2 new columns. Gain and speed are new columns created by just arithmetic on the old columns. And we can use the newly created columns in the same expression. So we create hours here, and then we use it here. We create gain here, and we use it here. But we can't do the reverse. I can't put gains per hour equals gains over hours up here at the top. I have to, the parser is going to read left to right, top to bottom. And instead of mutate, I can say transmute if I want to just keep the new variables. And of course, again, this doesn't do anything to your original data set. It's just if you want to save it as a new data set. Or you can always save and overwrite the original data set too. Useful creation functions. So you can do any of these things: arithmetic, modulus, logs, offsets, cumulative and rolling aggregates, logical comparisons, and ranking. So we're going to see an example of almost all of these. So here's an example of modulus arithmetic. So we're getting hour from the departure time. So the departure time could be like 1630. So we're doing integer division on that to get the 16 part. And then we're doing modulus on the minutes, so that for any amount. So why are we doing this? We're transmuting flights to get hour and minute. Oh, I know why we're doing this. We're going to see it a little bit later. Basically, this is just going to allow us to do time arithmetic. Here's an example of using logs. So we're going to create a new diamonds data set with the log to the base 2 of price and log to the base 2 of carat. And so we're going to do two plots. One plot is going to be with just price and carat, and the other one is going to be the log of price and log of carat. And we're using the geom called geom hex. This creates hex bins. Let me just show you. These little hexagons are called hex bins. And you can see, hopefully, that the second plot is easier to read than the first plot. So this first plot, apart from being curved, has most of the data centered right here, because most of the diamonds are less than 1 carat. Actually, most of the diamonds are less than 2 carats, less than 1.5 carats. I think this is where most of the data is. It's hard to see on here, but the lighter colored tiles reflect where there's more data. And similarly, the lighter colored tiles reflect where there's more data here. But because they're in these vertical stripes, it becomes obvious that there are certain weights, like 1 carat or half a carat or a third of a carat, that are very popular, because that's what people like to sell. The offset examples, lag x and lead x, I think those are the only two. So we can either look at data behind where we are or ahead of where we are. Useful in time series calculations. Cumulative aggregates, so we can do cumulative sum. And I'm sorry, I should have lined these up. So as you increase the data, you can get the sum of the reading from left to right of the data. So 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, and so on. And the same thing with the mean. You get the cumulative mean as you're going on. I should have lined these up. Sorry about that. Okay, so ranking. So there are a number of ranking functions, and it's good to know the difference. So here's the raw data, 1, 2, 2, 3, and 4. And here we have a tie for second place, and then the next place given is 4th place. Okay, that's min rank. The opposite of min rank is dense rank. So with dense rank, we have first place, then we have a tie for second place, and then 3rd place is given next. And row number is just row number. And min rank can be done the opposite. Min rank can be done in descending order. And percent rank just takes min rank and rescales it between 0 and 1. So this is the min rank just rescaled from 0 to 1. Okay, and there are some mutate exercises, and I should have done attach flights earlier in this slideshow. Sorry about that. That's kind of a. I think actually that was an exercise. Was how do you bring flights into focus? Here we're just taking the departure times that equal midnight and giving them a value of 0 instead of a value of 2400. Here we're doing that time arithmetic, so we have departure minutes, arrival minutes, so we can actually subtract the departure minutes from the arrival minutes and get airtime, get air minus dep and compare it to airtime. And be careful when you run this. This is going to give you 105 plots because of this facet wrap, because there are 105 destinations. Come to think of it, it may not give you all 105 because the destinations, let's see, will it give you all of them? This is just non-canceled flights, so if there are any destinations that don't have any non-canceled flights, the number will be smaller than 105, but it's a very large number. Okay, so more mutate exercises. So here's the delay ranking. We're taking the delayed ranking for the top 10. Less than 11 is going to give us 1 through 10. And we're arranging it by delay rank. So this is going to give us the top 10 most delayed flights throughout the year. Getting help on min rank. That's going to give us help on all the rankings. I don't remember this one. This one was just, what are the trigonometry functions? If you do this, you get nothing. If you do this, you get that trigonometry is supposed to be capitalized. So if you do this, you get the actual trigonometry functions. Summarize the fifth of 6 functions. So this collapses a data frame to a single row, but usually it doesn't. Usually it collapses it to a group of rows. So used by itself, it's going to collapse a data frame to a single row. And that's usually not what we want, because we can easily get something like the mean just by saying mean depth delay. We don't have to enclose it in all of this stuff. So what's going to make it useful is if we use it with group by, so the 6th of the 6 functions. So group by changes the unit of analysis from the entire data set into groups. So if we do what we just did, but we apply group by, then we get an average delay per day. And that's quite useful. Now, one thing I should mention is that this is a style of programming. Okay, so we've taken a function, we put it in a temporary variable, we use that temporary variable in the next line, and then we never use it again. That's, not necessarily the greatest way to do things. One alternative to that would be to take this whole thing here and put it in here. Some people wouldn't like that either. So the authors give us an alternative. So first they say, this is the boring way to do it. This is using temporary variables. So we do this, and we get a temporary variable of by dest. Then we use the temporary variable by dest, and we get the delay. Then we use the delay, and we get actually another delay. But this is a new variable, just happens to have the same name. It's a new concept. So that's one way to do things. Another way to do things is through a pipeline. So in this pipeline, we end up with delays. We start with flights. We pipe from flights to group by. We pipe from group by to summarize. We pipe from summarize to filter. And so these are the pipe characters that tell us that this is a pipeline, tell us that all 3 of these are participating in the pipeline, and then the last thing has to be participating in the pipeline because of this. So these 4 are all participating in the pipeline, and the final result is this. But notice that there are no intermediate variables here. That's the key takeaway. And the payoff is that we take that delays, that new delays data item, and we make a new plot from it. And that plot gives us the count of delays, delay by distance. So this is the distance of the flight. This is the size of the bubble is the number of flights at that distance, and the delay is just the average delay, the average flight delay. I think. Let me look at that. Yeah, average delay. Okay, so the result tells us that long flights make up time. You can see quite clearly here that if a flight is really long, they can make up time. Most of the delay happens on the runway as planes are stacked up. Okay, so the pipe is similar to the Unix pipe, but it's implemented as this incredibly ugly thing instead of the single bar character in Unix. And all the functions except ggplot2 can use it. And that's only because ggplot2 predates it. And in the book, the authors point out that there's going to be a new version of ggplot2 called ggviz that will allow the pipe character to be used. Although the book has been out for a year. I have not seen ggviz. I don't know if it exists yet or not. Missing values. So we're going to use this over and over again. So this, I can't seem to, I just want to highlight not canceled there, because we're going to use this not canceled over and over again. So we're taking flights and filtering out the canceled flights. So the canceled flights have no departure delay and no arrival delay. So those are not canceled flights. And then we can do things like grouping by year, month, and day, summarizing by mean. So that gives us a an average delay per day. And I think that's the same. Oh no, this is grouping them by tail number. So each plane is identified by its tail number, and there are, let's see, there are 3,322 planes represented in the data set, and this is a plot of the average delay per tail number. And you can see that it looks like there are a few planes with very, very large delays. So this is a little bit misleading. So let's investigate the details of the data to find out why it might be misleading. So we're going to summarize, again, delay by tail number, the average delay by tail number. And we're going to also just include the number of flights that the plane made. So we have its delay, which is its average delay, and the number of flights that it made. And we're going to do a scatter plot of that, and we're going to use a lot of transparency here. So this is very low opacity. 1/10 is very low opacity. So you can see, so each one of these circles represents a tail number. So each one of these circles represents a unique plane. And so some of these planes have just barely more than barely more than 0 flights. These probably had 1 flight, and they had a huge amount of delays. Planes that get flown a lot, so these are planes that have been flown, 400 times. This plane has been flown over 500 times during the course of the year. They don't have very big delays. And we can do the same thing with another data set. This is a little bit of an aside. We're going to go back to the flight data in a second, but the authors take a little bit of an aside. to show that players with a, well, let me just go right to it. Players with a better batting average are the ones who get to bat often. So this is number of times at bat. So each circle represents a player, and if they're, and this is the player's batting average. So if the player's batting average is really low, they don't get to be at bat very often. If the player's batting average is high, then they get to be at bat very much more frequently. Okay, so here are some summarizing examples: measures of location, spread, rank, position, and counts. So this is just a few examples of this that we'll finish up the chapter with. And all with the not canceled flights. So here's the average delay and the average positive delay. So this is average delay when the delay is greater than 0. Average delay can be negative. I mean, excuse me, what am I saying? Average delay? I meant arrival delay. Arrival delay can be negative. Distance to western destinations is more variable than others. And by others, we mean mostly East Coast destinations. We can find the first and last flights that leave each day. And here's another way to find the first and last flights. Instead of saying min and max, we just say first and last. And here's yet another way to do it, is by ranking them and simply getting the range of the ranks. We can find the destinations with the most carriers and arrange them by, if we arrange by descending carriers for this function just returns unique values. So this is the number of unique values for a particular destination for not canceled flights. Here's just a simple counting helper. This just will tell us the number of destinations for non-canceled flights. And we're counting one column based on another column. So counting tail number based on distance. Here we're using true and false as if they were 0 and 1. So n early is just going to what does n early do? I think this is a mistake on my part. I'm just going to skip that for the moment. Proportion of flights delayed by more than an hour. Hour percent mean arrival delay greater than 60. Okay, so that's just proportion of flights delayed by more than an hour. Flights per day, per month, per year. So we're just summarizing, creating per day, per month with summarizing function. Big delays and variable delays occur later in the day, so we can group them by the hour of the day, and with the exception of probably midnight. We changed midnight. I think we changed midnight earlier to be 0, so that is going to affect this. The most delayed and the most variably delayed planes. So this is going to group by the tail number of the planes. So this is the most delayed, and this is the most variably delayed. So this is SD is standard deviation. So that's the most variably delayed planes. Okay, and that's it. So I've left out the end of the chapter, but this slideshow has to come to an end, and I have covered all 6 of the functions in the chapter, at least to some extent. So don't take it as a substitute for reading the textbook, just use it as a supplement. And I thank you for your attention. Until next time.